In this module, we will be looking at a logic for expressing properties over computation trees. It's called computation tree logic star, CTL star. Let us start off with CTL star. A short recap of what we have seen so far. LTL is a logic that can express properties of paths. So a formulae of LTL can be called path formulae. LTL is just one way of expressing properties of paths. We could have generic path formulae to express more general properties of paths. To carry them over onto trees, we introduce the A and E operators for all paths and exists a path. And we also saw a way of mixing A and E to get interesting properties on trees. We will now define a logic for expressing properties on trees. Look at this tree. Each node in this tree is some state of a transition system and it is labeled with atomic propositions. Consider some state. What are the things that you can say on a state? So these are called state formulae. Let us see. You can evaluate true on a state. Every state satisfies true. For every atomic proposition, each atomic proposition Pi is a state formula. You can evaluate it on a state. So this state satisfies red. Similarly, look at this state. Each state, you look at the label of that state. Suppose the label of this state is P1, P2, then this state satisfies the state formula P1. These are characteristics of states. Given two state formulae, suppose I know that some state formula is true on this state and some other state formula is true on that state, you can make an AND of these two, phi1 and phi2. Similarly, you can make a NOT as well. So these are the things that you can evaluate on a state. True is true on every state. P1 will be true on the states which have the label P1. Similarly, P2 would be true on the states which are labeled by P2. You can form ANDs and NOTs. You can say P1 and not P3, for instance. Okay, these are all properties which can be evaluated on the state itself. And hence they are called state formulae. Let us now look at path formulae. The things that you can talk over paths. So alpha is a path formula if it is of the following forms. Suppose you look at a state formula. You can also evaluate it on a path and say that this path satisfies this formula phi if the initial state satisfies this state formula. For example, look at the state formula P1 and not P3. We can say that this path satisfies P1 and not P3 if this initial state satisfies P1 and not P3. This is the same way we defined LTL formulae. So every state formula can be looked at as a path formula as well, and the meaning of that is that the first state satisfies this formula. If you have two path formulae, you can make AND and NOT of it. If this path satisfies both alpha 1 and alpha 2, then you can say that it satisfies alpha 1 and alpha 2. Suppose this path does not satisfy alpha 1, then you can say that it satisfies NOT of alpha 1. These are the temporal operators. Now start the temporal operators. You can say on this path that x of alpha 1 is true. That means the path starting from this position satisfies alpha 1. This is same like LTL. You can also say alpha 1 until alpha 2. So these are all paths, these are all evaluated on paths. Alpha 1 until alpha 2, x of alpha 1 and so on. You can also talk about f and g which are derived out of until, but still let me write them down as f alpha 1, g alpha 1 just for clarity. So you can look at a path, this path satisfies g red. Similarly, some other path will satisfy f of some p1 and so on. So these are all formulae that can be evaluated on paths. Now let us get back to state formulae. So these were the state formulae, P1, P1 and not P2, P1 and P3 and so on. We saw path properties. Where do A and E fit? You can say E of alpha on a state. So given a state, you can say that E of a path formula is true on this state, right? That means there exists a path that satisfies alpha. So E alpha is actually a property of the state. It's a characteristic of the state. So E alpha is a state formula. You need to understand this. These are all easily state formulae. What about E alpha? Look at this state. You can evaluate E alpha on this state. And E alpha will be true on the state if there exists a path that satisfies alpha. Okay. Similarly, A alpha is again a state formula because it's a property of it's a characteristic of the state. All paths starting from the state satisfy alpha. So path formulae are the ones which involve the temporal operators x until f and g. And state formulae have this quantification over paths, E and A. Okay. This is called CTL Star. CTL Star is made up of state formulae as well as path formulae. This is a mutually recursive definition because you see alpha uses state formulae and state formulae use alpha again. Okay. So CTL star is made up of state formulae and path formulae. Let us look at certain examples. You can say E of alpha, and alpha can be f of some path formula again, which could be phi, and phi could be p1. So you know how you get EFP1? Let me repeat. So EFP1 is a valid state formula because a state formula, see, look at EFP1. It is of the form E of alpha, right? Where alpha is f of some alpha 1. Look at this, alpha 1 could be phi and phi could be p1. So that is how you get EFP1. What about AFAGP1? This is again a state formula because it's of the form A alpha, where alpha is f of AGP1. Look at this. It can be f of alpha 1. So AGP1 should be obtained on some alpha 1, but this is, for this you use the fact that alpha can be one of the state formulas. And here you can use A, so you get AFA of alpha, where alpha is GP1 now. Okay, and you know how to get GP1. So this is a valid formula that can be obtained out of this syntax. This is the syntax of CTL star, and you can derive this from this syntax. What about AFGP2? See, P2, okay, let's start from here. It's a state formula because it's of the form A of alpha, where alpha is FGP2. This says that FGP2 says that it's a property of a path. It says that in this path, at some point of time, rather from some point of time, P2 is always true. This is FGP2. From some point of time, GP2 is true, and this is true over all paths. So A of alpha, where alpha is a path formula, FGP2. How can you form FGP2 here? F of alpha 1, where alpha 1 could again be G of something, and finally this something is a state formula where you have P2. So AFGP2 can be derived using these rules. These are just rules of deriving formulae. You can also say AP1. Let's see the meaning of this later, but you can say A of alpha, where alpha could be a state formula and the state formula is P1. You can also do this, AEP1, because A of alpha, alpha could be a state formula which could be E of alpha, and again alpha could be a state formula P1. Okay, so these are all valid formulae of CTL star. This is giving us the syntax of CTL star. Any string that can be derived out of these rules is called a CTL star formula, and it could either be a state formula or a path formula. Let us now try to attach meanings to these strings. We saw certain examples and we saw what they mean in the last module. However, let us try to give a precise definition to each of the strings. So we ask this question. State formulas are evaluated on states in the tree. So when does a state in a tree satisfy a state formula? This is the question that we ask. These are the state formulae. Every state in the tree satisfies true. A state satisfies Pi if its label contains Pi. So this state will satisfy red. For example, if this state has P1, P2, then it satisfies P1 and it also satisfies P2. A state satisfies phi1 and phi2 if it satisfies both the state formulae phi1 and phi2. Similarly, a state satisfies not of phi1 if it does not satisfy the state formula phi1. What about this? A state satisfies E alpha if there exists a path starting from the state which satisfies alpha. I mean, the path starting from the state should satisfy alpha. We have seen this before. Similarly, a state satisfies A alpha if all paths starting from that state satisfy alpha. This could be any state in the tree, not necessarily the initial state. A state formula can be evaluated in any state of the tree. And this is the semantics. This is the meaning of these formulae. And this slide answers the question, when does a state in a tree satisfy a state formula? Now, what about the path formulae? When does a path in a tree satisfy a path formula? This path could start from any state. I've just given this for illustration. You have a path starting from some state, and when does this path satisfy a path formula? So these are the possible path formulae. Most important is this base case. When does a path satisfy the state formula phi? Path satisfies phi if the initial state of the path satisfies phi. Okay, Suppose you have a path starting from this state, say, and you have a state formula P1 and P3. This path will satisfy it if this state satisfies P1 and P3. The state formula could also be AX something, and the path starting from this will satisfy the state formula if the initial state satisfies the state formula. Okay. The rest are standard. A path satisfies alpha 1 and alpha 2 if it satisfies both of them. It does not, it satisfies not of alpha 1 if it does not satisfy alpha 1. For X, U, F and G, it's standard like LTL, so I do not want to repeat. Now, we saw when a state in a tree satisfies a state formula, when a path in a tree satisfies a path formula, and now when does a tree, suppose you're given just the tree and the state formula, when does the tree satisfy the state formula? We say that a tree satisfies state formula phi if its root satisfies phi. So this tree satisfies, say, AF P1 if from every path starting from the root FP1 is true. So let us see some more examples. EFP1 exists a path starting from the root. When it's not mentioned, you can assume that the path starts from the root. Exists a path where FP1 is true. That means where P1 is true sometime. What about this? AFAGP1. This is a valid formula. We saw how it is derived. Now what does it mean? In all paths, there exists a state where AGP1 is true. This is for AF. In all paths, there exists a state where AGP1 is true. In all paths starting from the root, there exists a state where AGP1 is true. In all paths, there exists a state from which all paths satisfy GP1. Right? That is the meaning of AGP1. Now, this just means that in all paths, there exists a state such that every state in the subtree below it contains P1. Okay? This is the meaning of AFAG. In all paths, there exists a state up to this AF such that every state in the subtree below it contains P1. This is for AGP1. What about AFGP2? In all paths, there exists a state where GP2 is true. That means P2 is true forever starting from that state. In all paths, there exists a state from which P2 is true forever. What about AP1? All paths satisfy P1. That means all paths start with a state labeled with P1. This is true as the state formula P1 itself because it just needs the root to satisfy P1. And if you evaluate the state formula P1 on the tree, it means that you're evaluating it on the initial state. So AP1 is actually the same as P1. So these are some examples of the properties expressed using CTL star. Let us now re-look the examples of the previous module with this additional semantics defined. EFAG exists a path that reaches a state, see FAG red. So there exists a path where f of AG red is true. That means that means there exists a state where AG red is true, and this is that state. AG red is a state formula. AFAG, we have seen this before. So from all paths, there exists a state that satisfies AG red. EGEX, there exists a path such that every state satisfies the state formula EX red. So this satisfies EX red, this satisfies EX red, this satisfies EX red, and so on. So EX red is a state formula, GEX red is a path formula, and EGEX red is again a state formula. This is one more tree which satisfies EGEX red. Now this is, see, EX blue is a state formula. Similarly, AG red is a state formula. And this until this is a path formula, which is true on this path. This state satisfies EX blue, this state satisfies EX blue, this state satisfies AG red. So this path satisfies EX blue until AG red, and E of this is again a state formula which is true on this state. So there exists a path satisfying this until formula. Now, so far what we have seen is, we have given you the logic CTL star made up of state and path formulae. We saw when a tree is said to satisfy a CTL star state formula. It is said to satisfy this state formula if the initial state, the root, satisfies it. Finally, what we are interested in is a transition system. Given a transition system and a CTL star formula, when do we say that the transition system satisfies the CTL star formula? Easy. The transition system satisfies CTL star formula phi if its computation tree satisfies phi. That means you have to evaluate the CTL star formula on this initial state, on this root, and if the formula is true on this tree, then this transition system is said to satisfy the CTL star property. Let's now ask a different question. We saw property specification using LTL. Now we are seeing property specification using CTL star. Can the properties which can be expressed using LTL be written using CTL star? Let us see. Recall that a transition system satisfies the LTL formula if the traces of the transition system, that is all paths, satisfy the formula phi. In other words, the traces is contained inside words of phi. We have seen this many times before. So this LTL formula gives rise to a set of words, and this transition system's traces is again a set of words. This set should be contained in this set. That means all paths in the computation tree satisfy the path formula phi. If you look at this computation tree, paths in this, traces correspond to paths here. Paths of this transition system correspond to paths of this computation tree. And by saying that every path satisfies the formula, we are just saying that every path in this computation tree satisfies the path formula phi. Hence, the LTL formula phi is the same as the CTL star formula A phi. If you evaluate, in other words, if the transition system satisfies the LTL formula phi, the computation tree of the transition system will satisfy A phi. Similarly, if the computation tree satisfies A phi, then the transition system will satisfy the LTL formula phi. So, the answer is LTL properties can indeed be expressed using CTL star. Now, what about the reverse question? Can CTL star properties be written using LTL? As in, if I want to talk something about the tree, can I write it using LTL, which deals only about paths? As you might have guessed, the answer is no. Look at a property like this. You want to say that in the transition system there exists a path from which all possible continuations satisfy certain property. This kind of a mix cannot be expressed using LTL. It needs CTL star. So this says that there exists a computation which reaches some state from which all possible extensions satisfy a certain property. In this module, we have seen the logic CTL star, which is made of path and state formulae. You need to understand the distinction between this. Please go through the examples once again if you have not understood this. We have shown that LTL properties can be expressed using CTL star properties. And in fact, this is a strict containment in the sense that there are CTL star properties which cannot be expressed using LTL properties.